In today's video, we'll be going over Bernoulli's principle.
So Bernoulli's equation says this. The pressure plus 1/2 rho, which is density, v, which is velocity squared, equals a constant. The main idea is that if velocity changes, pressure changes. So across Gyro's cloak, the pressure difference is written like this. The change in pressure equals 1/2 rho velocity at the top squared minus velocity at the bottom squared. Now we need to model the air speeds. So if you let V be the headwind and let Vs be the surface speed of the spinning steel ball, we'll write this. Equals omega r, rotational velocity and the radius of the ball. Now, not all of that spin transfers into the air. Even in the scene, you can see air going everywhere and his cape fluttering. So we have to put in an efficiency coefficient. Not all of that spin transfers into the air, so we must include an efficiency coefficient. So the velocity of the top equals the headwind. K will be our efficiency coefficient times the velocity of the surface. Velocity of the bottom equals the headwind minus the coefficient times the velocity of the surface. So plugging those into Bernoulli's equation gives this. Change in pressure equals 1/2 times the density multiplied by the headwind plus the coefficient times the surface velocity squared minus the headwind times the coefficient, the headwind minus the coefficient times the velocity of the surface. Square all that. And using basic algebra, this simplifies down to 2 times the density times the velocity times the efficiency times the velocity of the surface. And since the velocity of the surface equals omega r, you can then write the equation like this. So pressure times area gives us a force, and lift is a force. So our lift force can be written as lift equals the change in pressure times the area over which it's acting. So this would be the area of the cloak. And our really big final equation will be what your lift force actually equals. So the values we're going to use are standard conditions, and we're using metric. The assumption of the headwind from Santa Ana is 18 meters per second. The efficiency we'll be using is about 5%, which is common for messier scenarios like this. The rotational velocity was revealed to me in a dream, and it is this value. The radius, this is in meters, is also revealed to me in a dream. The area of his cloak, we're assuming to be 0.2 meters squared. If you plug all this in, you get a lift of about 102.3 newtons. So basically, the lift he is causing himself to experience is about 102.3 newtons of force. This load is no longer on the horse, which allows the horse to run faster. So we can actually figure out how much his mass was quote unquote reduced by simply using this formula. So the lift is the force up, gravity is the force down. You just divide the two. So he reduced his mass effectively by 10.4 kilograms, or about 23 pounds.